the area of a circle that has radius 1 is pi times 1 squared, which is pi. So one way of approximating pi is by approximating the area of a circle with polygons. So here is an inscribed hexagon, and if I draw this triangle here, this is 1. These are all radii, 1, 1. This is an equilateral triangle, so that's 1. This is equilateral because this arc is 1/6 of the circle. This angle has to be a 60-degree angle. And to get the area of this triangle, I could draw in the altitude. It's a 30, 60, 90 triangle, or you can use Pythagorean theorem if you know this is 1. If you know this is 1, this is a half, then you can do Pythagorean theorem to get the square root of 3 over 2. So the area of the hexagon is 6 of these triangles, and each triangle is 1/2 base times height. I'll make this the base and this the height. You end up with about 2.598 round to 1. So what we can say now for sure is that pi is greater than 2.5981. But we can do better than that by having by instead extending this side and drawing this line segment in. And this triangle here that I just drew, this one, is 1/12 of a dodecagon. So if I could find the area of this triangle, which I'll just shade red right now, if I could find the area of that triangle, multiply it by 12, then I can get a better approximation for pi. Well, it seems tricky, this triangle. It's an isosceles triangle, and it seems like I don't know the base or the height if I were to draw this altitude. But the good news is I don't have to make the base of the isosceles triangle the base when calculating out the area. Instead, I'm going to call this the base of the triangle, which would make this the triangle's height. And the good news about that is I know the base is the radius of the circle, so that's 1. And the height, what I'm calling the height here, is half of this length, that length was 1, so this is a half. So for the decagon, for the dodecagon, the area is 12 times 1/2. The base I'm going to use, this is the base, is 1, times 1/2. And that becomes 3. So the area of the 12-sided figure is 3, and now I have an even better approximation for pi. I could say pi is bigger than 3. It's also bigger than 2.5981. Now, one way of getting a better approximation is by having more sides, and we can and we will do that. But what Liu Hui figured out is that with these two calculations, the 6-gon and the 12-gon, I could actually also get what's called an upper bound for pi. So pi is bigger than 3, but how much bigger than 3? Well, I'm going to show you a clever method that he figured out of how to use these two values to get an upper bound for pi also. The observation is that pi is definitely bigger than this area of this dodecagon, but it's also less than the area of this figure, which is the hexagon plus the 6 rectangles. So I'm going to even write down, so pi is bigger than the 12-gon, but less than the hexagon plus these 6 rectangles. So if I could figure out the hexagon plus the 6 rectangles, that would give me an upper bound. And this picture shows the clever idea. So we're trying to figure out, so we have that pi is bigger than the 12gon and less than the hexagon plus the 6 rectangles. But I've split those rectangles up, each one into 3 triangles. So I want you to notice that each rectangle, 6 rectangles, is equal to 6 of these red triangles plus these 12 little yellow triangles. But if you look carefully at this, you'll see that this is a rectangle and this is the midpoint of the top. So the 2 yellow, the red triangles half the rectangle, and the yellow 2 triangles add up to half. So the 6 rectangles together are actually equal to 12 of those red triangles, because each rectangle is equal to 2 red triangles. So now I could take this expression and say pi is bigger than the 12gon and less than the hexagon plus 12 red triangles. But now look carefully. If you just take the dodecagon, which is the green and the red added together, and you subtract away the green, the hexagon, you're left with 6 rectangles. So I'm going to write another thing on the side. I'm going to say decagon, or 12gon, minus the hexagon is equal to 6 red triangles, which means 12 red triangles would be 2 of these 12gons minus 2 hexagons. Well, finally, I can take, not finally, second to last step, I could replace the 12 red triangles with 2 12gons minus 2 hexagons. I still have this hexagon from before. When I combine everything together, I get that pi is bigger than the 12gon, but less than, see, this hexagon minus 2 hexagons is negative 1 hexagon, and this 2 times 12gon. So I get this relationship, which I'm going to write down neater on another page. So pi is bigger than the 12gon, which you might remember was 3, but it's less than 2 times the 12gon minus 1 times the hexagon. So in this case, that's 2 times 3 minus, that's times 3, minus 2.5981. And then when you do that, 6 minus that, you end up with 3.4. So we have pi between 3 and 3.4. In general, the rule is, like if I were to do this again, somehow get the 24gon, I would then say that pi is bigger than the 24gon, but less than 2 times the 24gon minus 1 12gon. Or some people say, in general, it's bigger than a 2n-gon, but less than 2 times that same 2n-gon minus a regular n-gon. So with this method, you can get really good approximations for pi, and as a challenge, you should try to get the next level, which is 3.1058 and 3.2116. That would require this diagram. So we've already established that this is a half and this is 1, and this is a half also. Now, in order to go to the next level, and we would need to know the length of CB. CB is important because FB is the height of this little OEB triangle, which is 1/24 of the 24gon. So what I would have to do is look at this picture. This is square root of 3 over 2. And OC is 1. So if I subtract this little piece here, I can get CD. CD is 1 minus square root of 3 over 2, which is about 0.13397. So now I have this little right triangle, CDB, which has 0.13397, and it has a half as its other leg, which means that CB is the square root of 0.5 squared plus 0.13397 squared. Which ends up being about 0.51764. That's what CB is. Now, our goal was to find the area of this triangle here. That's the 24gon. So what I'm going to do the same trick as before. I'm going to call this side the base, which is 1. So we're going to do 24 times 1/2 times base, and the height is this little line segment here, which I guess is FB. That's going to be half of the 0.51764, which is 0.25882. And when I multiply all that together, I get 3.1058. So with this, I could say that pi is bigger than 3.10582, but less than double this, 3.10582, minus 1 dodecagon, which is 3. So if I multiply that by 2 and subtract 3, I get my better approximation, which is 3.2116. That's how we got that other calculation.